Now, as we've already seen single populations in discrete times, what if we wanted to look at two populations at the same time and how they interacted with each other? Examples of this are predator-prey models, parasites or parasitoids, and other such examples. We consider governing equations, in this case, of the form nt plus 1 is equal to some function of nt and pt, and pt plus 1 is equal to another function of nt and pt, where nt and nt plus 1 are populations of the first species in time t and t plus 1 respectively, and p is the other population. As before, we want to find key behaviours in the system, so we will look for fixed points in the system. The definition of a fixed point is given by supposing that n star and p star is a fixed point of the governing equation. This implies that nt plus 1 is equal to nt equal to n star, and pt plus 1 is equal to pt p star. Like in single populations, by first considering 0, 0, and then if this is biologically possible or relevant, n star p star, we can then look at when n star p star doesn't equal 0. Through rearrangement, it is again possible to find the other fixed points in the system. To look at this example, we shall look at the Nicholas-Bailey model, which states that nt plus 1 is equal to r0 times nt times some function f, which is nt and pt, and then the population for pt plus 1 is equal to c times nt times 1 minus the same function of nt and pt. If we happen to set f is equal to e to the power of minus apt, then we have the model. So this gives us equation 1, nt plus 1 is equal to r0 times nt times e to the minus apt, and equation 2, pt plus 1 is equal to c times nt times 1 minus e to the minus apt. Suppose that n star p star is a fixed point. We can then say that n star equals nt equals nt plus 1, p star equals pt plus 1. So then we'll look at n star, which is equal to r0 times n star times e to the minus ap star, and p star equals c times n star, all times by 1 minus e to the minus ap star. Supposing that n star equals 0 is a solution, this gives us that 0 is equal to is a solution, is equal to 0, and we then look at when n star equals 0, what does p star equal, and it happens that this equals 0. So now we will suppose that n star is not equal to 0. This implies that 1 is equal to r0 times e to the minus ap star. This can be rearranged to 1 over r0 is equal to e to the minus ap star, and then using logarithms and rules of logarithms, we can get that minus natural log of r0 is equal to minus ap star, which can rearrange to give p star is equal to 1 over a natural logarithm of r0. Now we visit equation 2, and when n star doesn't equal 0, p star is equal to the 1 over a ln r0, as we just acquired. So we plug these into the relevant points, so we end up with 1 over a natural log of r0 is equal to c times n star 1 minus e to the minus natural logarithm of r0. This is the same as saying equal to c times n star all times by 1 minus 1 over r0. So n star is equal to r0 times natural log of r0 all divided by a times c all times by r0 minus 1. So now we've found the two fixed points of the system, we can say that 0, 0 and r0 times ln r0 over ac r0 minus 1 and 1 over a times natural log of r0 is the other fixed point in the system. Note that this is only biologically relevant for when r0 is greater than 1, otherwise we would end up with negative numbers, and that's not possible in a system.